Hello, my name is Aditya and I'm from JMSS. I'll be presenting my solution to problem number 11, balls on an elastic band. So let's take a look at the problem statement. Connect two metal balls with an elastic band, then twist the elastic band and put the balls on the table. The balls will begin to spin in one direction, then in the other. Explain this phenomenon and investigate how the behavior of such a pendulum depends on the relevant parameters. So let's take an overview of the model. First, we'll go over some theoretical model, and then we will talk about some qualitative description of the energy transformations taking place, and we will try to quantify the energy transformations. And then we will take a look at the experimental model and drop on some conclusions based on what factors this phenomenon depends upon. So let's introduce a theoretical model where we have taken two hollow spheres of mass m and each of radius r, and they're connected by a rubber band of rest length L. And the second image is the side view of one of the balls, and it's when the ball is twisted through an initial angular displacement of theta naught, and theta is the angular displacement in later time t. So, and we can also observe that an angular displacement of 2 pi radians is equal to 1 turn. So we can make a very nice relation between the number of turns in the band to the initial angular displacement. The n turns will be equal to 2 n pi radians, and as the number of turns increase, a tension force arises in the rubber band inwards, attempting to contract the length of the rubber band. And if we hold the band when we twist it, we can feel a tension force attempting to contract the length of the band. And there's also a video demonstration visible which shows the phenomenon in action. So now let's talk about the moment of inertia. So the moment of inertia is defined about the axis passing through the center of the spheres. So as we can see that there's one sphere on the bottom right here, there's another sphere on the other end, and basically the blue axis passing through the center of these spheres is the moment of inertia the axis that the moment of inertia is defined about. So we can take an elemental region dx and then integrate over the entire region to find an expression for the moment of inertia, and we get 2 by 3 mr squared. We can add the 2 by 3 mr squared of the other ball, as moment of inertia is a scalar. So we get the total moment of inertia of the system is 4 on 3 mr squared. Now these values are obtained assuming negligible mass of the rubber band, and according to the experimental model that will be later introduced, the mass of each ball is 28 grams and the radius is 0.075 centimeters, and so the moment of inertia is 2.1 times 10 to the power minus 6 kilogram meter squared. So let's talk about torsional acceleration without friction. So ignoring friction at first, and let's see what happens when we don't ignore friction, when we don't take friction into account. So a restoring torque arises in the rubber band when we twist it through an initial angular displacement. And when we put it on the table, the net torque on the system is just that restoring torque put by the rubber band on it. And that restoring torque is equal to minus k theta, where k is the torsional constant, and the net torque is defined to be as the moment of inertia times the angular acceleration. So we get this differential equation by taking the k theta to the other side and factoring out the I and dividing both sides by I. And this is the second order differential equation, which is the standard differential equation for simple harmonic motion. So this is concrete evidence that this motion is an example of simple harmonic motion. Now we can solve the solution, so we can solve the differential equation and obtain these solutions. Using the initial conditions, we can obtain a function for theta, and we can differentiate both sides and multiply both sides by r, and now we have a function for the tangential velocity. So, and omega naught here is defined to be the natural frequency of the oscillator as square root of k on I, where k again is the torsional constant, and the time period of such an oscillator is 2 pi divided by the frequency of it, and the frequency here is the natural frequency since there is no damping, so this is 2 pi squared I on k. So these graphs show that the equations obtained in the previous slide actually make intuitive sense. So as we can see, angular displacement, if you have an initial angular displacement of, let's say, 60 pi, then with time it goes down and increases in the opposite direction, and this process goes on to infinity, which is clear in these graphs here. And the same is seen with the speed of the balls as well, as that also keeps oscillating in opposite directions to infinity since there is no damping present. So now let's introduce damping and see what happens and what that does to this motion. So let's introduce a damping force which is linearly proportional to its angular velocity. And now when we put the system down on the resting surface, the net torque on the system is the restoring torque and also the torque put by the damping force. So now the modified differential equation will be written as a minus k theta and minus v theta dot, and the minus stands for that both of these torques are in the opposite direction of the actual initial angular displacement. We can take both terms to the other side, factor out the i's, and now we get the standard second order differential equation for damped simple harmonic motion. we can solve this solution. We can solve this differential equation for the underdamped case, and we obtain a solution of this sort, and where omega dash is the damped angular frequency. Figure 2 shows just an example of an underdamped oscillation. That has nothing to do with theta in this context, but that's just an example of what underdamped oscillation might look like. So now we can find the values of A and phi using the initial conditions that at t equals 0, the angular displacement is theta naught, and the first derivative of theta at t equals 0 is 0. So we can now write the function of theta. So this shows what the angular displacement is at any time t if it's rotated by an initial angular displacement of theta naught. So let's talk about the energy transformations. It's clear that the energy oscillates from elastic potential energy to rotational kinetic energy and translational kinetic energy. Now the reason that translational kinetic energy is in there is because it's rolling motion, and rolling motion, each particle is rotating as well as translating, so it has both types of kinetic energies. And this motion would go on forever until the initial elastic potential energy is dissipated by the non-conservative force of friction. So now let's try to look at the total energy of this oscillator. We know that total energy will be equal to kinetic energy plus potential energy, and we obtain this expression by a very standard derivation by putting in half m and then basically deriving the angular displacement, putting that into that equation. And then for the underdamped case, the ratio b on 2i is much smaller than the natural angular frequency, so the cosine term can just be neglected, and then the total energy just becomes half I a squared omega naught squared, and the exponential term. So this really shows that the total energy of the system is actually exponentially decaying. And figure 3 shows an example of this process happening, that the total energy of this oscillator is actually decaying with time until it finally becomes 0, and at t equals 0, the total energy is the elastic potential energy stored in the band. So now the experimental model was introduced to find the torsional constant, which was done by basically suspending known moment of inertia I naught by rubber band and by clamping the other end, and the known moment of inertia was calculated to be 2.8 times 10 to the power minus 6, and basically the sphere was set into torsional oscillations, and the time period was calculated for 5 trials to find out the amount of time it took for it to do one oscillation, and the equation t equals to 2 pi squared I on k was used. We basically rearranged the equation for k, and we obtained this expression, and we put in the values, and we got an answer for k, which is 3 times 10 to the power of minus 6 Newton meters per radians. Now this value is incredibly small, and it makes sense for it to be small because this basically shows how much torque is needed to twist the rubber band by 1 radians. And as we know, that it doesn't require a lot of force for us to twist a rubber band, so that makes intuitive sense. Now determining a damping coefficient using experimental methods. Now, the graph below shows the tangential velocity, which is obtained experimentally by using a tracker software, and the exponential function was found as a regression function, and it was basically it was fitted to this function, and the regression function was found to be of the form y is approximately equal to a to e to the power of minus 1.1 t. So we can clearly see that the zeta ratio here, which is b on 2i, is 1.1, and basically we can multiply both sides by 2i and obtain the value of b. So now the damped angular frequency is obviously omega dash equals squared q and I, and we can put in the values, we get an answer of 0.47. So the damped time period must be around 13.4 seconds. So this is our theoretical prediction that when we measure the time period of this oscillation, it should be roughly around there. The time period could also be affected by the factors such as air resistance, and also the rubber band's torsional constant decreasing as more and more oscillations are done using it. So here was the experimental model, and basically the time period was actually measured to be around 13.9 seconds, and this shows that it was really close to our theoretical prediction, which was around 13.4 seconds, with the deviation being of only about 3 plus 3% or minus 3%, which can be obviously due to other external factors. But for the most part, there were also other 2 trials done, trial number 2 and trial number 3, and the experimental time period was around 13.5 and 14.2. So all of these values are relatively close to our theoretical prediction. So this graph is just, again, an indication of how the tangential velocity of each ball is decreasing with time, and an exponential decay is clear. So coming on to the conclusion and talking about what factors this phenomenon depends on. So firstly, let's talk about the most important factor that this phenomenon depends upon, which is the moment of inertia. And moment of inertia is essential to this phenomenon as it is responsible for the ball's overshooting past the mean position. And the entire reason of the ball's actually overshooting past the mean position is the moment of inertia. So the higher the moment of inertia, the more oscillations are likely to take place. And as we saw earlier, the moment of inertia was 4 by 3 mr squared, so it only depends on the mass and radius of the balls, which means the larger diameter balls will also tend to do more oscillations. And as we can see in this very nice graphical visual here, that as the slider of the moment of inertia increases, so the moment of inertia increases, and the number of oscillations increase as well. So the angular displacement increases, and so does the total number of oscillations. So coming on to these three photos on the top, the first image shows that if the balls are glass balls, so they don't have enough high enough moment of inertia, then the rubber band will basically twist up, as shown in the image below. It will basically wind up on itself, and there won't be many oscillations taking place. But when metal balls, such as in the second picture, are used, or the third picture, where balls of larger diameter are used, the mr squared, the r is greater, there's more moment of inertia, and the system oscillates higher and higher. However, there is a limit, because if the moment of inertia is very high, then again there will be no oscillations, which can also be seen in the graph of the angular displacement. Other factors include damping and resistance. So the damping also needs to be in the correct proportion, which is clear from the angular displacement equations. If it's not in the correct proportion, then well, there won't be any oscillations taking place, such as if the moment of inertia is too great. Other forms of resistance could also affect this harmonic oscillator, and also torsion constant of the elastic band, as if the torsion constant is small, it is easier for the system to oscillate as less torque is required for an angular displacement to happen. However, if the torsional constant is too low, the initial energy stored in the rubber band may be dissipated by friction at a faster rate. So these were the references for this presentation, and thank you all for listening.